Let me.
Good evening, sir.
What should we discuss? Please help me decide what to discuss. Let us decide what to discuss. It's open to discussion. So tutorials can be led by the participants. In fact, everything can be led by the participants. So if you have any questions, anything particular that we want to do, we'll do that first. Yes. Guruswami, maybe you should please let me share screen.
Okay, sir. So already you are a co-host only, sir.
எனக்கு host disabled participant screen sharing anu varudhe.
Varume, sir. Sir, now try.
Ipo varudhe.
Okay, sir.
Okay, so I'm sharing this whiteboard.
Yes, sir. Your screen is visible, sir.
Okay, please let's start.
Okay, sir.
Which problem do you want me to want us to discuss? Yes.
Number of conjugacy in symmetric groups we already discussed.
Yes, very good, very good. I wanted you to just say it. Yes, very good. Let's discuss that.
Okay, sir. So
okay, go ahead. Anything else?
Okay, sir. Suppose conjugacy in Sn is equal to the number of partition of n. This is the
correct
number of conjugacy classes in Sn.
Yes. Yes.
Suppose 1 plus, suppose n equal to 5, partition of n, 1 plus 1 plus 1 plus 1, etc. plus 1, which is equal to identity element only occur. After that, 1 plus 1 plus 1, 3 times, and plus 2, cycle of order 2. The number of element conjugate to this this type of cycles is
okay
equal to
okay, you're talking about the homework problem that number 3 or something.
Yeah, sir.
Very good. That's
yes,
a very
sir.
good problem. So okay, so which do you want to discuss first?
The product that is 1 plus 2 plus 2, this type of cycles, sir. So order 3, order 2, order 3, it is easy, sir. But
okay, let's do. Okay, so here is the question. I guess all of you can see this. Let me choose some different color. Okay, question. Okay, so how many? So let us take S5 in S5, right? You were saying, for example, how many elements are conjugate to say 1, 2, right? So what is your answer, madam? How do we do this?
Number of element of order 2 is equal to the elements in conjugate class of this number of elements in this conjugate class.
Well, why is that? Why is that? So
sorry, because 1, 2, and 3, 4 also have a order 2.
Right.
Length 2. Sorry.
Yeah. No. So the theorem that we know is the theorem.
1 plus 1,
so
1 plus 1 plus 2 of the cycle type have a...
Correct. So theorem, remember the theorem, and we last time in the tutorial, I think we gave a proof of this also. This is that 2 elements in Sn
The number of elements
are conjugate if and only if they have the same cycle type, right? If and only if, it's an if and only if they have the same cycle type. So let us first list some of the elements that are conjugate to this. For example, 1, 2.
1, 2,
1,
3,
2.
4.
So some conjugates. Okay. 1, 2.
Cycle of length 2.
Yes. 1, 2, 3, 4. You can, whenever
1,
you can
3,
write 1, 3, 1, 4, 1,
1,
5,
4.
etc. Right?
Yes, sir.
Right. So how many are there? So in this case, maybe we can even do it like this. So,
Yes, sir.
so how many
In
are there?
first.
1, 2, 1, 3, 1, 4 up to 1, 5. Right?
Yes, sir.
Right. And then 2, 3,
2, 3,
2,
2,
4,
4, 2.
2, 5. I don't count 2, 1 because 2, 1 is here. Right? Already counted. Okay. 3, 4,
3, 5.
3, 5, 4, 5. That
4,
is 1
5.
plus 2 plus 3 plus 4. Right? Here is 4, 3,
Yeah.
2, 1. So total is 10. Right? We can do it this way.
Yeah.
But can we do it a little more?
First we have 5 choices, sir. So 5 into 4.
Okay, in the first position you have 5 choices. Okay, so I want to write something like A comma B, right?
A comma B.
Okay,
First
first
position we
position
have
is
5
5
choices.
choices, right?
Second
Right.
position 4 choices.
4 choices, right?
Divided
So
by
give you
2.
20. Why divided by 2?
Because AB equal to BA.
Very good. So that's another way of doing it. So what you're saying is, look at all, let me not write this. Yeah, okay. So AB, but observe that this is also equal to, this will also appear as BA, right? So 5, 4, 2, 5, so indeed,
Divided by 2.
this is the right answer. Okay. And I think the explanation you gave is very good. 5 cross 4 is the number of ways you can write two elements AB, right?
Yes.
Is the number of sequences you can write. But then if we count the number of sequences, we will be over counting, because the sequence AB is also we don't want to count sequences. We want to count these elements AB, the cycle. So if I get this sequence 1, 5, that's the same as that this element is the same as this element, right? So that's why I divide by 2 and the answer is 10, right? Very good. Very good. Okay. Now, another way of thinking about it is the following. So this a single cycle is determined by the choice of 2 elements. You just need to pick 2 elements from 1, 2, 3, 4, 5, right? It doesn't matter which order, right? And that is 5C2 or 5 choose 2 written like this, and which is also 5 cross 4 divided 5 into 4 divided by 2, which is 10. That's another way of thinking about this problem. Okay, so good. So, but this is only a very baby case. Madam, please, what else did you try? Let's try. How about 1, 2? So, conjugate to conjugacy, number of conjugates of this cycle 1, 2, 3 in SI. Or if you want to write it like this, let's do this. I've taken SN now, but if you want, you can try n equal to 5 first to be, or even n equal to 4 first before we answer this question. Madam, you said that you had solved this. Can we hear your solution, please?
NC3. So NC3.
Okay. So you're choosing 3 elements. Okay. NC3. Is that the answer, or?
position, that is 1 plus 1 plus etc. So position of 1, 2.
So let us say I choose
that's
A,
also
B,
NC.
C are my elements, right? In no particular order. So that will be, that is NC3. Okay, now what do you do with this? So with 3 elements A, B, C, how many 3 cycles can I form?
NC3.
Well, no, well, you have to be a little more careful. So see, what NC3 gives you is how many subsets of, so NC3 equals the number of subsets of order of cardinality 3 or order 3 of 1 through n. It is the number of subsets of cardinality 3 of 1 through n. Okay. But given a subset, how many 3 cycles can I make?
3.
Okay. What are those? Please, let's write those. I'm give you A, B, C, or even 1, 2, 3. Let's say. How many can you make? What are the 3? Oh, the answer was 3. So let us look at it.
1, 2, 3.
1, 2, 3.
1, 3, 2.
1, 3, 2.
And no. Only 2.
Anything else? Okay, here is the thing to observe. These are all. You can only form 2.
Only 2.
Why is that? Because you can always choose the first element to be 1. Right? You choose 1. You can always write your cycle with 1 as the starting element. No problem at all. Right? The next element can be one of either 2 or 3. So it can, you 1, 2, 1, 3, and the third element is determined. So there is exactly 2 for every choice of 1, 2, A, B, C. Either you can choose one of these and let it be the first element. So this is one cycle I can form with it, or this is another cycle I can form with it. These are the only 2 that I can form. So what is our final answer here? So to answer this question, what is the answer? NC3 into
2.
2. Very good. Okay. So that's if you want n into n minus 1 into n minus 2 divided by 1 times 2 times 3 into 2. These 2 cancels. So it's n into n minus 1 into n minus 2 divided by 3. Okay, very good. Okay, you want to try something else? Let's try number of conjugates of 1, 2, 3, 4 in Sn.
Then combination 4 into 3 factorial.
4 into 3 factorial. Okay, let's see. Yeah, okay. So please tell me the answer, sir.
N combination 4.
NC4. Okay.
Into 3 factorial.
So this is see, I'm using this notation, but this is also written. Usually the Americans don't write this notation. They say write n choose 4. Both are the same thing. Okay. N choose 4 and then
into 3 factorial.
Into, okay. So sorry. So let me. So this is an aside. So answer is, okay. Let me in the previous case also, let me This is our answer, final answer. This is our final answer in this case. Answer is n choose 4 or NC4 into 3 factorial is the claim. Okay, why so? Can you please give us the reason why you think so?
If I'm taking the one on first position,
Yes.
so one can go for the one has the 3 options to move further, either 2, 3, or 4.
Mm-hmm.
And suppose if one goes to 2, then the second element having the 2 options.
Very good.
So that's
Very
why
good.
3 into
So,
2, 6.
very good. Excellent. So once you have, so this is the number of choices of 4 elements. So I choose, this gives me a choice of 4 elements, A, B, C, D, in no particular order, right? That's different choices of these 4 elements are counted by this n choose 4. Okay, next, what do I have to do? Given a particular choice, I have to see in how many different cycles I can make out of it. Okay, and as in this case, previous case, we observe that one of them, say A, you can always take it to be the first element, right? You can always take it to be the first element, and then it's a question of arranging B, C, D in some order, right? In various order. Every order that you can write them in will produce a different cycle. Therefore, you are counting the number of permutations of 3 elements, which is 3 factorial. Okay, so this is n choose 4 into 3 factorial. So let me leave it like this. Or let's see. I also want to write it. So it's n. Yeah, just let me leave it like this. Okay, you can simplify this, but doesn't matter. Okay, let's do another case. So let me not lead the discussion. Please, is there a case you want to do? Next, which case do you want to try? Hello? I am hearing no reply. So
Disjoint.
disjoint. Okay, please. Okay, let's have an example. What kind of cycle do you want to try?
In S7, 1, 2, 3, 4, 5, 6,
Okay.
7. Like this.
You want to try that? Okay. How about? Are you sure you want to? So the one thing in mathematics, the problem is very general. It is asking for any cycle type in any n, right? That's what the problem is asking for. Correct. And you handled it by breaking it up into various cases, so simple cases. And indeed, that's the right thing to do, because if we are trying simple case, having any progress. Okay, so so number of conjugates of okay, you gave a slightly. How about I try this only in a cell? I am simplifying your suggestion. Instead of taking 1, 2, and then 3, 4 into 5, 6, 7, we'll come to that in a minute. How? Let's do just with 1, 2, 3, 4. Okay. So now how do we do this?
7 combination 4 into 4 combination 2.
Let us not, whatever you do, then it is going to be one such answer, right? It is going to be, let us get our logic straight, okay? Rather than try to guess the answer. Okay, so how are we going to count this? So you were suggesting something, but I'm just
First
asking
we
for
select-
more. Go ahead.
First
Go
we
ahead, sir.
select 4 elements.
First, you select 4 elements. So that's NC4 or 7C4. Let me write NC4, right? Let's do it more generally. Okay. So this is 4 elements. Let's say A, B, C, D. Okay. Then?
And for getting same cycle structure,
Mhm.
so I am selecting 2 elements for one group and 2 elements for the other. That's
Very
why
good. So you choose 2 elements for one group. Okay.
4 combination of 2 ways.
4 combination 2. Okay. 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 Then did I write down what you said correctly, or is there anything else?
It is correct.
It is correct. Okay. So indeed, I agree with this. So it's A, B, C, D. Choose 4, right? And then you choose 2 of them, right? So this will count. We have to make sure that that we have not over counted and we have counted everything. Have we counted everything? Now we need to think a little bit. So let us do that individually. I agree with this answer. Do you? Are
1
we all
by
confident?
2 into 4 combination 2.
Sorry, say that, sir.
I think 1 by 2 one factor will be there.
Why?
Because in 4 combination of 2, I'm selecting 1, 2 one time. Okay. And other time I'm selecting 3, 4.
Right. So indeed. So here AB. So once I choose AB and then CD is chosen, right? So this you're saying should be multiplied by 1/2. Now that's you modified that, right? Okay, but is this correct now? Can somebody venture an answer, please? You know, one way I feel that you can check these answers is by just trying it out in a small case. So let's put n equal to 4 and try it. There, what answer do I expect? Like for n equal to 4, how many of these are there? Can somebody tell me, please, how many of these are there for n equal to 4?
3.
3. 1, 2, 3, 4. It's just a question of what you put with 1, that's all, right? The other thing is determined. So here we get 4 choose 4, 4C2 into 1/2, which works out to be 1 cross 6 cross 1/2, which is 3. It seems to give me the right answer. Okay. How about n equal to 5? Let's try for n equal to 5. If I try this, what do I get? So 1, 2, 3, 4, 1, 2, 3, 5, 1, 2, 4, 5. Right? And so on. Already it's getting complicated maybe, but let's maybe 1, 3, 2, 4, 1, 3, 2, 5, 1, 3, 4, 5. Right? So as we can see, this is counting the first, sorry. Yeah, this is counting which 4 I'm choosing. For example, 1, 2, 3, 4, etc. And then with once you have chosen 1, 2, 3, 4, you can make. Okay, let's convince ourselves that this is the right answer by just saying, once I have chosen 4 elements, I can make 3 combinations out of it, 3 different cycles, like here. Or with ABCD, it will be ABCD, AC, BD, and AD, BC. Okay, so this is the right answer. So let's put a marker on this. Okay, at least I think this is the right answer. Do all of you agree?
Yes.
Okay, good. So let us just think about it in a slightly different way. Can we do that, please? Can we slightly? I want to think about this in a slightly different way. So that way is here as follows. See, it's important in when you would solve problems. Just because you have solved a problem, it's not the end of the story. You can try to solve the same problem in different ways. Now, why is this useful? One of the reasons is that when you encounter a harder problem, often it gets solved by only one of these other methods. So if you have a simple problem, maybe there are 10 ways of doing it. A harder problem may have fewer ways of solving it. And for example, if the numbers are small, often you can do just by brute force, and you can come up with the answer. But that will not work for larger numbers. So you need some argument, and there may be several different arguments, different types of arguments, and only maybe some of these arguments generalize, not all of them generalize. So it is good for us to think about different ways of solving the same problem. So let us look at it differently. So here is how I want to look at NC2, right? So that is choose 2 elements, right? And choose another 2 elements, but from n minus 2 C2, right? Another 2 elements. These 2 elements will form the first cycle. These 2 elements will form the second cycle, right? But again, there is a repeat, because these 2 elements I could have chosen here, and these 2 elements I could have chosen here. So you can also write this, right? This is another way of thinking about it. Okay, so let's make sure that these 2, since I'm saying this is the answer and this is the answer also, this is also an answer, let's make sure that these 2 numbers are the same, right? So what is NC4? It is n into n minus 1 into n minus 2 into n minus 3 by 1, 2, 3, 4 into, this turned out to be 3, right? 3. So this is on the one hand, and we are asking whether it's equal to this, which is what? N into n minus 1 by 2. Okay, this is n minus 2 into n minus 3 by 2 into 1/2. Okay. So indeed, this is correct, because I'm getting 8 in the denominator here and 8 in the denominator here. So this is also okay. This is another way of thinking and getting the same answer. Rather than choosing all the 4 to begin with, you can choose 2 of them to start with and another 2 next. But then you have to put this n minus 2. Okay, very good. So let's do one more case. Number of conjugates. I'm going to the suggestion given by madam of 1, 2, 3, 4, 5, 6, 7. Let's do this in SN. She was saying S7. We can do this in S7 if you want, but let's do it in SN. So what is the answer here? Let me go to a different. Yeah, please start. Please suggest some answers for me, please. So we are doing a number of conjugates of 1, 2, 3, 4, 5, 6, 7. Yes. How do we do this? Any suggestions?
7 combination 2 into 5 combination 3.
Okay, let me put SN. So let's think more generally. Go ahead, sir. First, you want to choose 2 elements. N combination 2. Right. Okay.
Now n minus 2 combination 3.
N minus 2 combination 3. Okay.
Then multiply by 2. Multiply by 2.
What happened to the other one? What happened to this?
Oh, sorry. N minus 5 by n minus 5.
N minus 5.
Combination 2.
Combination 2. Okay. And then
multiply by 1 by 2.
Multiply by 1 by 2. And what is the reason for your choice here, sir?
Because if suppose in n combination of 2, I am selecting 1, 2.
Yeah.
Okay. And in 5 combination of 2, in n minus 5 combination of 2, I am selecting 3, 4. That is one possibility. But it is also possible that in n combination of 2, I am selecting 3, 4.
So here, this choice and this choice, if I choose AB here and CD here, or CD here and AB here, that's an overcount, you're saying.
Yes, that's a
okay.
Okay, and again multiply by 2, because in the cycle of length 3, for the choice 5, 6, 7, there will be 2 such cycles are possible.
Right. So this choice of 5, 6, 7 will give rise to either 5, 6, 7 or 5, 7, 6. Right. So you're going to multiply that by 2. So you're explaining. So, okay, though here is the explanation. Let me repeat. Sir, I don't know your name. Could you tell me your name?
Ranjit, sir.
Ranjit. Okay. So Ranjit is suggesting the following solution. You first take these 1, 2. That's this NC2. Please correct me, Ranjit, if I am not saying correctly what you meant to say. Right?
Okay, sir.
Then he is choosing this 3. Of course, you can choose this one or this one. Doesn't matter. The order doesn't matter. So n minus 2 CG gives you the 3 elements with which you to do this. And these 2 elements he is choosing. We've already chosen 5 elements, right? These 2. And so 2 more from n minus 5 C2. And then I multiply by 1/2. The reason being, these 2 I have repeated. The reason being, if I choose AB here and CD here, then I will overcount, because I could have chosen CD here and AB here to get the same element. So this 1/2 takes care of the overcount with respect to these 2 choices. And this 5, 6, 7 gives rise to 2 choices, because once I choose 3 elements, 5, 6, 7, I then have 5, 6, 7 and 5, 7, 6, 2 possibilities for upright. I agree with this. So you can just list this out, and for S7, for example, you can try to count whether we are doing this right. Okay. So anything else you want to try? This still doesn't solve the problem fully. So is there a next complicated case you want to try? So number of conjugates of What should we try? Let me try 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm putting comma here just to, with single digits, I need not put a comma. Here I am putting comma because these are 2-digit numbers, nothing else. I mean, this is still the cycle 10 going to 11, 11 goes to 12, 12 goes to 10 in SM. Sorry, in SM. Now, what is the logic? How do we do this? You just continue. One possibility is just continue the same kind of thing.
N combination 2.
N combination 2. Okay.
Then N minus 2 combination 2.
N minus 2 combination 2.
N minus 4 combination 2.
N minus 4 combination 2.
Multiply by 1 upon 3 factorial.
Multiply by 1 upon 3 factorial. And why so, sir?
Because see, in the first choice I am selecting 1, 2, then 3, 4, 5, 6. It might be possible that I'm selecting 3, 4 on first position, 1, 2 on next position.
And 5, 6. Very good. Excellent. So I agree with you. I hope this argument was clear to everybody. So he's choosing these three, making these three choices. But of course, I could make the choice instead of taking 1, 2 first, 3, 4 next, and 5, 6 third. I could have made 3, 4 first, 1, 2 next, and 5, 6 third. But those two would give me the same cycle. I would be overcounting. And there are 3 factorial because I can arrange these 3 in 3 factorial ways, right? So that is 1 over 3 factorial indeed. And then
N minus 6.
N minus 6.
Combination 3.
Combination 3.
Then N minus 9.
N minus 9.
Combination.
N minus, sorry. No, this is N minus 6. Okay, you're right. N minus 9 combination.
Combination 3.
Okay.
Into 1 by 2.
Into 1 by 2.
Into 2.
And why is that 1 by 2, sir?
Again, sir, if I'm in the first one, I'm selecting 7, 8, 9. In the the second time I'm selecting 10, 11, 12, or
Okay.
it is also
So
possible that
with your permission, let me write 1 over 2 factorial here because that's okay.
Okay, sir.
That's a slightly better way of saying it. 2 is the
Into
same as 2
2.
factorial. But the thing is, it will remind us that if I have 3 of them, then I need to put 3 factorial there as well. Correct?
Yes.
Okay. Into
2 into 2.
Into 2 into 2. Very good. And why is that?
From the selection 7, 8, 9, we can obtain 2 cycle.
Right.
Similarly for the next one.
Similarly for the next one. Very good. So indeed, this is the right answer. Okay. So, however, okay, this way of thinking about it, will this help us in solving the problem as it is stated? So, as it is stated, there is a certain formula that is claimed, right? In the exercise sheet, there is a certain formula that is claimed. Okay, so let's do the following. For now, we have worked enough on this problem. So let's today stop working more on this problem. And let me invite you all to look at, so we have learned something new, hopefully, and try using what we have learned, the reasoning behind these as the solutions of these, to solve the problem as it is stated in the tutorial sheet. Okay, there is still a gap between where we are and where we need to be. There is more thinking for you to be done. Maybe you have already done it, but those of you who have not done the problem, finished the problem, please go back now again to that problem, and with the help of what we have done here, maybe you need to think slightly differently also, if necessary, and finish the problem. Is this okay? Can we move on to some other problem? Because we have spent some time discussing this. We will come back to this problem. This is a very important problem. And if we solve this problem fully, the problem in the tutorial sheet, I'll be very satisfied with that, because it's one of the tough problems. Okay. So is this good? So should we discuss something else, please, now? Is that a good suggestion?
Yes, sir.
Okay. So let's discuss some other problem from the tutorial sheet, or some other place. I'm waiting for your suggestions. Are all the remaining problems are all okay in the tutorial sheet, or? For these tutorials, I repeat, I need your help and cooperation. Even for the lectures, I need your cooperation, but for the tutorials, even more so, because I want you to lead the tutorials. I want you to lead the discussion. Go ahead, madam.
So in Sn,
Yes,
so
and
sigma is element sigma.
yeah.
So number of element commute with Sn.
Okay.
How to find the number
How
of
to do
element
that?
commute
Okay.
with this.
Okay. So right. Okay. So there is a question also. Number of elements that commute with sigma in Sn, right? With a given. Okay. I give you some cycle type, some sigma. Say this one: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many of them come? Okay. So this problem was a bit premature. Okay. But this gives me an opportunity to describe how we want to solve this. Okay. So let me say, I'll tell you how the key to this solution. I intended to cover this in yesterday's lecture, but didn't get that far. We just stopped short of it. So if you recall, this is a good time to do it. In yesterday's lecture, we finished with this. So G by Gx is isomorphic to G. Pay close attention to where the X is. Here is a subscript, here it is an X on the side. Okay. So this is the orbit of X. This is the coset space, and this is the stabilizer of X. Okay, so it goes without saying that G is a group, and which is acting on a set X, and G by stabilizer of a point X is a point in X, fixed point. You have fixed a point X, little x, and so this is the stabilizer of this little x in G. Meaning all those elements, let's recall the definition, G sub X is all those elements of the group which fix this given element. And we had seen yesterday that this is a subgroup of G. And Gx is the orbit. Okay, so let us look at this orbit of X in X. So what this tells us in particular is that this is an isomorphism, and this is what is called a G isomorphism. That is, there is an action of G on this, there is an action of G on this side, and there is an isomorphism which respects the G action. But that is not so important for us for the moment. What is important for us is that these two sets have the same cardinality. That's the corollary of this. So this is a corollary of this statement, that these two sets have the same cardinality. Okay. Now let us look at the following. Let us take G to be Sn. Okay, and it is acting on itself. X also to be Sn. Okay, and G acting on X as follows. So G X, let me write it like this, is Gx G inverse. So it's acting by conjugation. Okay, that is the action. Then suppose I give you an element X, which is an element of Sn. What is the orbit? What is the orbit of X? So what is Gx in this context? In this context, meaning in this example.
Conjugates of X.
Conjugates of X. So the orbit, let's be a little more precise. The orbit is precisely the conjugacy class of X. Of X. So let's put this X equal to, so for more clarity, let's put this X equal to sigma, right? Just for, right? I'm using this sigma that you're doing, okay? So conjugacy, so X equal to sigma is the conjugacy class of sigma. Okay, so what is this? What is the cardinality of this? What is, so in other words, what are we counting here? So this is the number of conjugates of sigma, right? So number of conjugates of sigma, that's the left-hand side. Sorry, right-hand side is equal to, now this is a coset space, so I can write this as G by G, the stabilizer at sigma. Now let me write sigma here. Okay. Now what is G sigma? Anybody please? What is G sigma? G sub sigma. So this is a G sub X and this is G X on the side. So this is G sub sigma.
Normalized of sigma.
Which is?
Centralizer of sigma.
Which is all those elements that commute with sigma. That is the language we used, right? Okay. So this is by definition. Let us look at this definition. It was written here. Gx is equal to X, where this is the action map, right? So that action map is Gx G inverse. Okay, you should not get confused by this notation. This is here, in this context, say here is this Gx does not mean G plainly multiplies X. That doesn't make sense in general. This is because X is a set here. So this Gx denotes the action of G on sigma, whatever that action is. So in our definition here, the action is Gx G inverse. So what we have is G sigma is nothing but all those G in G or G in Sn, such that G sigma G inverse is equal to sigma. This you can also write as G sigma equal to sigma G, right? Therefore, this is just nothing but, this cardinality is nothing but number of permutations or elements of number of, let me write elements of number of elements of Sn that commute with sigma. Okay, so we have this formula. Now this is as an application of what we did. So this G this becomes n factorial in our case by number of, so let me write it slightly, instead of writing at a quotient, let me write it like this. See this, from here you get the following. Applying this is number of elements that commute with sigma times number of conjugates of sigma. So this is a beautiful relation between the number of elements in, this in any group. In fact, let me write it. In any group, you have this G is equal to, so G is a group and X is any element in the group. X is an element of G. Then the cardinality of G, let's say finite group. It's actually true also in the infinite case if you appropriately interpret things, but never mind. G is finite group. So this is the number of elements that commute with with X times number of elements that are conjugate to X. Which is, in other words, the cardinality of the conjugacy class, this latter one. Okay, so you have this beautiful relationship, and exploiting this relationship, you can answer that other question, second half of that question. Is this clear, madam? Have I answered your question?
Yes, sir. So
Okay.
it is possible to find that element particularly for given sigma.
Okay. That's a good question. And I think, okay, that's a good question. I think directly doing that is difficult. The logic for that would be, it should be possible, but I think it is much harder. I hope all of you understood her question. That's a very beautiful question. So she's asking, instead of using this relationship, can we just directly do this? Is that your question, madam? Did I say that correctly?
Yes, sir.
Okay. And my reply is that I don't know how to do that directly. It may be possible, but it's going to be a much tougher permutation combination problem. So for the moment, I don't know. I need to think about it. But the point is that this is the point. See, you can do it directly perhaps, but look here. This is a general relationship between those two objects. What commutes with X, as Annamalai called it, the centralizer of X, right? The centralizer, all those elements that commute with X on the one hand, and the conjugacy class of X on the other. These two are reciprocal in terms of, that is, with respect to the cardinality of the group. That is, they together they multiply to give the cardinality of the group. This is a relationship which is very fundamental and very beautiful. And so if you disregard this relationship, then you are losing something. So I'm not suggesting that you should only do this problem this way and you should not try it directly, but I am suggesting that when there is such a fundamental and beautiful relationship and you try to exploit it, then that gives you an added instrument in your toolkit. It is an extra device, a tool in your toolbox. So I hope I have conveyed to you, madam, that using this is a very good thing. One of the takeaways from this course that I would like you to take away from this course is such calculations and this relationship. So is this clear? Because in doing it directly is more difficult, I think. And also there is why not use this? Because this can be used in various different contexts as well. So have I answered your question once again, madam?
Yes, sir.
Okay.
So the question is finding number of elements commute with sigma, right?
Yeah. So
we know that disjoint permutation commute.
Disjoint permutations commute, yes.
So suppose if you take sigma as some cycle type.
Okay. So the question is, what all, for example, you try to do what all commute with 1, 2, right? Okay.
In SN or some?
In SN, yeah.
Okay, in SN. So
centralizer of, okay, let's call this something. It's okay. So I'll call Z sigma.
So I say in general, sir. So
okay. Yeah, go ahead. Sigma, yeah, go ahead.
If you take any sigma, suppose the cycle length is M cycle. Suppose you take M cycle in SN.
Yeah, M cycle.
In SN, sigma say M cycle.
Let's say 4 cycle.
Yeah, 4 cycle. In SN. So we know the theorem that any disjoint permutation commutes.
Right, correct.
And we know the order of the permutation is 4. Therefore, the powers of permutation also commute with itself.
Yeah.
Therefore, the remainings are n minus 4 elements. We have already took 4 1. The other possible permutation is if you take any permutation other than these 4 elements. If you take, that means if you take any elements in Sn minus 4.
In Sn?
Minus 4. The permutation
okay. Sn minus 4, okay.
Therefore, if you take all the possible permutation in Sn minus 4, all the permutations commute with this permutation.
So you take Sn minus 4, all those commute with this.
That is n minus 1 factorial.
N minus 4 factorial, yes, correct.
All the permutation commutes with this.
Okay, all the permutations commute here, okay. And then?
Now we can add the number of, the order of the permutation. You can add.
So you are saying plus how many? 4.
And 3. So because we already count the identity element in the Sn minus 4.
Okay, you want to add 3. Okay.
Yeah.
So is this your answer?
Yes.
Okay. How about the following? 1, 2, 3, 4. This cycle times 5, 6, 7, 8. Have you counted that here?
Yes, sir. This is one of the permutation in Sn minus 4.
Where is this in plus 3? So you have counted here. Here you have counted this.
Yeah.
Here you have counted this. But where have you counted the product? Where have you counted the product?
Yeah, you got to multiply. 3 times.
Okay, you want to multiply. Okay, and then how about something else like so you're modified now. This is your answer. Is that what
1, 2, 3, 4? Again 1, 2, 3, 4, 5, 6 only. Also commute with 1, 2, 3, 4.
Say that again. 1, 2, 3, 4.
1, 2, 3, 4. Another permutation 1, 2, 3, 4, 5, 6, 7, 8. Also commute with.
Yeah, exactly. That's the discussion we are doing. So 1, 2, 3, 4, and that's the discussion. For example, like this also commutes with this.
Yeah, that is nothing but sigma square times, sir.
Sorry.
So 2 times of n minus 4 factorial.
Why 2 times n minus 4 factorial? Because he's now taking product here.
Okay.
He's taking.
So suppose if call it as alpha. Suppose alpha equal to 1, 2, 3, 4.
So see, is this your answer then?
Yes.
Okay. I'm afraid I'm not convinced. First of all.
Yeah.
Okay. So you can try this in a slightly more complicated case and try it out. Okay. The arguments are going to be maybe not so easy. It is possible, perhaps. I like I said, I don't know. I don't recall. It may be possible. So try it by all means. Okay. So there is a lot of cases to be considered. Right. And if it gets more complicated, if it gets more complicated, then it's See, it's not only disjoint cycles that commute. Cycles that are not disjoint can also commute. That's the issue.
That is the power of the permutation.
Well, there may be other things. There may be other things in the, So, for example, you take 1, 2, 3, 4 into 5, 6, 7, 8, right? There may be, for example, various, for example, 1, 2, 3, 4, 5, 6, 7, 8 will commute with this. But this is not a power of this permutation. You see that? This is not a power of this permutation. It's only, this is a power of this. But you understand what I'm saying? So, for example, 1, 2, 3, 4, 5, 6, 7, 8 will commute with this permutation. But this is not a power of this permutation. So, see, if I may make a suggestion, Annamalai, so having these ideas is very good, but what we need to do is check. So follow this up. You may have an idea, but we need to check this against examples and see if the idea is right or it will go through. I hope I'm making sense. Okay, so I am not stopping you from trying it directly. By all means, do it, and we'll listen to your solution. Except that once you have an idea, you should try it out and see if it is correct. Can you prove it? Or if you're not able to prove it, or even before proving it, try it in a few examples to see whether this is giving a correct count or whether there is a problem or something. Okay. Okay. So that's a very good, we've learned something. I don't know if we are out of time or we can go on for a few more minutes. Dr. Gurusamy, what do you suggest?
Okay, sir. Continue, sir.
4 minutes, sir.
Continue. Okay.
Continue.
So,
Okay, sir.
okay. So we can go on for a few minutes. Okay, sure. So what else do you want us to discuss now? So should we call this over for now today? That is this problem. So we know how to solve the number of elements, compute the number of elements that commute with a given permutation by using this formula or this nice relationship. I don't want to call it a formula. It is a formula, all right, but rather this beautiful relationship between the stabilizer and the orbit, right? And using that, we can, and our previous exercise about how to go about computing the number of elements that are conjugate to X, combined with that, we can compute the number of elements that commute with X. The question was how to do this directly, but for that we are saying it may be a little difficult, but you are welcome to try. Okay, so anything else you want to discuss now? I'm waiting for your suggestions. Gurusamy, if I may make a suggestion.
Okay, sir. Tell me, sir.
So since it's 1 hour, I think we should let people who have other work to do
Okay,
feel
sir.
free to leave, but I will stay here. And
Okay,
if it is okay with you,
Oh,
and those of us who want to continue the discussion and want to ask some other question can do so, no problem.
okay,
How
sir.
about that? So people should not be forced to stay because they may have other work to do. We should respect that.
Okay, okay, sir.
So those of you who have other engagements or want to leave or just want to leave, that's fine. Officially, the tutorial is over.
Over. Okay, sir.
But I'll be here. I'm happy to continue this discussion if you wish, for those of you who want to stay back. And then,
Okay, sir.
yeah, okay. So any other discussion we want to do, we can, I'm happy to answer questions, more questions, or continue the discussion in any which way you think is beneficial. But you have to drive it. You have to suggest what we want to discuss.
one more thing.
Sure, sure.
Suppose we are done everything in Sn. What about if we take An?
Okay. What about An? Okay, that's a good question. Okay, so how about conjugacy classes in An?
Shall we apply the stabilizer orbit theorem in this group?
You can always apply the stabilizer orbit theorem. You can, it's because it's in general true that the, in fact, as G sets, the coset space of the stabilizer is isomorphic to the orbit of X as a G set. So this is a G map. So in particular, it is true that the numbers G, so let me write it like this. G is equal to the cardinality of G is the cardinality of the stabilizer times the cardinality of the orbit. This is a very important relationship, I repeat. This is one of the things that I hope you will take back with you from this course. And this can be used in various contexts. In particular, it can be used in this context. So, for example, but you need somewhere to begin. So, for example, what are conjugacy classes in AN, you can ask. I mean, is it just the cycle type, or do I need something else that you can ask? So not only in the alternating group, that's a very good question, but in any group and any X, any G, you can apply this. So in particular, this means order of G. So this is for any action. This is true for any action. And if I take the conjugacy action, this is for any action. For any action of G on any set X, and for any X in X. So it's very general, where this represents the stabilizer subgroup and this represents the orbit of X. In particular, so you apply to G acting on itself by conjugation. So if you apply it to this context, then you get this special case that order of G is a number of centralizer of, let me write it like this, centralizer of an element X. So X is any element of G. X, any element of G, times the number of the conjugacy class of G, of X, sorry, conjugacy class of X. This is a special case of this formula. And this is a very powerful formula. Okay. So, so for example, the illustration is computing this centralizer is you may be able to do it directly, but it's not going to be easy. So it transfers a difficult problem, the computation of the centralizer, for example, into an easy problem, which is the easier problem, let me say, to the conjugacy class of number of elements in the conjugacy class of X. In some other context, maybe the centralizer is the easier one, the conjugacy class is the more difficult one, right? So there are all different ways of various ways of using this, right? So it is indeed it's a very fundamental, this relationship between the stabilizer and the orbit is a very fundamental one in mathematics. So that is the emphasis I want to make. So have I at least partly answered your question, Anamale?
Yes.
Okay. You can try this. It's a very good idea. Maybe I'll put this as a homework problem, conjugacy classes in AM. That's a very good suggestion. Yeah, I'll put this in the next.
And one more thing, if you any other easy method to find the maximum element in AN or SN?
What do you mean by maximal element?
Maximum order element.
Okay. So you want to find the maximum order element.
Yes.
Element in SN. Wow. Okay.
What is the maximum order?
Yeah. So maximum order of an element in SN. Got it. That's what I meant. Yeah. Aha. So I don't know off the top of my head. Let me see.
That is LCM should be high. If you take the.
Is it? What did you say?
Because we know the order of the element is nothing but LCM of the length.
Yeah. No, I don't know off the top of my head. This depends on. This is more number theoretic, more in Anirban's territory than mine. I don't know the answer off the top of my head. Yeah, you just look at the cycle time and then take the G series of the different things involved. Yeah, different. So the question is, what is the maximum GCD I can get out of some parts of N, right? You have a partition of N, and what is the maximum GCD I can get out?
Maximum LCM.
Maximum LCM, sorry, right, maximum LCM. Correct. Thanks for correcting me. Maximum LCM that you can get out of this. Correct, absolutely. Maximum LCM I can get out of this. And I don't know that off the top of my head. And I don't know whether this idea of, I don't know if there is anything in group actions that is applicable to this problem. I will think about it. That's a good question. I'll see if I can. No, I don't know. Any other questions you want to discuss?
So suppose we can extend this, instead of taking single groups, if we take the Cartesian product of two groups and finding the conjugate classes in SN cross SM.
Very good. So conjugacy classes. In SN cross SN. Okay, let's try that. That's a very good.
SM are different.
Different M. Okay, very good. SN cross SN. Okay, so that's a very good question. How about that? Okay, this formula, remember, it holds here as well. It holds in all. It holds in all.
So, but how to define this conjugation up here? So action is conjugation action.
The action is conjugation, so you know how it is a group. So
okay, component based conjugation. Or?
So yeah, so if I have a G cross H, right? Two groups G and H. So what are the conjugacy classes in G cross H? Let's ask that question. So what are the conjugacy classes here? So for example, how many conjugacy classes are there? Suppose I know the number of conjugacy classes here, the number of conjugacy classes here. How many conjugacy classes are there in G cross H?
Be the product of.
Which will be the product, because you see, because you can conjugate this element to wherever. So see, this is G comma H, right? And these are, in a sense, I'm taking direct product. So these two are independent. So if G comma H is conjugate to G prime comma H prime, right? Let's say X conjugates G to G prime, which I write like this. This stands, remember, for XG X inverse, and Y conjugates H to H prime. Then XY will conjugate GH to G prime H prime. So G prime H prime is a conjugate of G comma H if and only if G prime is a conjugate of G and H is a conjugate of H prime. Right. So this kind of, when it's a direct product, the answer is not so deep. So you can work out conjugacy classes in Sn cross Sm. So two elements are conjugate if this permutation of n elements. So if I'm given sigma tau, one where sigma is a permutation of n, tau is a permutation of m, and another one sigma prime tau prime. This is conjugate to this if and only if sigma is conjugate to sigma prime and tau is conjugate to tau prime. And in the case of the permutation group, I know that this means sigma and sigma prime have the same cycle type and tau prime have the same cycle type. So that's not maybe so difficult. But that's a very good question. Right? And remember, this holds in any group for any action. So this is a very general formula. So this applies in various contexts. For example, you can apply it here. In fact, it's quite easy. So to compute what commutes with G comma H, I need to just compute what commutes with G and then what commutes with H and take their product. Right. So the centralizer of, so let me write it Z. Z is equal to the centralizer. If I use that notation, Z of G comma H is ZG cross direct product ZH. So I take the centralizer of G, which is a subgroup of Sn, centralizer of, or more generally subgroup of capital G, this ZH, which is a subgroup of H, and then take their direct product, which is a subgroup of the direct product G cross H, and that is the centralizer of G comma H. So that's fairly easy to understand, but that's a very good question. And one thing I appreciate, Annamalai, that you're doing this. You're asking lots of such questions, and indeed, I at least in my point of view, mathematics consists of asking such questions ourselves and trying out answers. That is a very important part of learning mathematics and understanding mathematics. So very good. You're trying, all these questions are very interesting. Any other discussion you want to have?
The existence of the subgroup of in Sn.
Mm-hmm.
In Lagrange's theorem, we have devices, the possibilities of the
good question.
existence.
Good question. Okay.
But
okay. So I don't know off the top of my head what the answer is. So let me form your question like this. Does converse of Lagrange's theorem, of course, it does not hold in general, but Lagrange's theorem hold for Sn, right? That's your question.
SI does not hold, but when it is possible to find.
Okay, do you know why does it not hold here in Sn? Is that clear? Why it does not hold?
In A4, it does not exist as a group of.
That is A4. A4.
6.
We are not. It does not. Converse of Lagrange's theorem does not hold in general. That we know. Okay, as you say in A4. Okay, it does not have a subgroup of order 6. Right, A4 is order 12, but it does not have a subgroup of order 6. But in Sn, do we know? Is this clear? I don't know the answer for Sn. If you know, let me know.
No, sir.
I don't know the answer in Sn. This is a very good question. It's a very good question. Maybe we can think about it. I don't want to venture an answer. I'm starting to think about it. I've never thought of this question. It's a nice question. Yeah, that's a very good question. I don't know. No? Or so you have an example, Annamalai?
S4. S4.
S4.
So the order is 4 factorial anyway.
Yeah, 4 factorial.
12 divides 4 factorial.
12 divides 4 factorial.
I think there is no subgroup of order.
A4? What is A4?
Is there? Oh, sorry. Okay. Sorry.
Yeah.
But if we take prime, and that is always if SP.
Yeah. Yeah. If you take SP,
then always.
So why is it obvious?
So if you take any divisor of P factorial, we have to find this.
Yeah. Any divisor of P factorial, you have to find a subgroup. Yeah. I've never thought of this question. It seems nice. Very nice question. I don't know the answer off the top of my head, madam. We'll think about this. It's a nice question.
So, okay, in this case, if we take M is a divisor of P factorial, then M is maybe we take the product of two numbers.
Product of?
Some numbers.
Yeah.
Therefore, that number should be less than or equal to P. Suppose M equal to A into B.
Yeah.
And then both A and B should be less than or equal to P. Because it's P factorial.
So you are writing A into B and A as prime factors, or what are you writing?
Not a prime factor. Suppose I take M is a divisor of P factorial.
Yeah.
We have to find a subgroup of order M.
Yeah. And if I write it as A times B, then?
Suppose M equal to product of two numbers, A, B, anything. But both A and B should be less than.
I mean, you are claiming
suppose
that. Yeah. Are you claiming that, or are you just checking that case?
I am taking this case. Suppose.
Okay, you're taking that case. Okay. So if A and B are less than P, okay, let's say they are, I don't know, P minus 5 and P minus 5, something like that. Yeah.
Distinct.
Okay, take them distinct. Yeah. If they add up to less than P, then it is easy, maybe.
Yeah.
Okay, then you can take just a cycle of order A and a cycle of order B, right? That's the easy case. But these things that divide n factorial can be very complicated, right? So
there is partially true, that is Silos.
Yeah, there is Silos theorem, of course. Yeah. But that is only for prime powers of that divide, prime powers that divide, yeah. Anyway, so this is a good question. However, I don't know if it has anything to do with the subject matter that we are doing. So I don't want to discourage this question. This is nice, but I don't want to give priority, however, to this question, because unless you bring in some group actions into this. Okay, let me put it that way. This is a nice question, no doubt, but should we discuss this? Should we give a priority? Should we spend time on it? I don't know. But if any of you have some idea how to solve it, of course, we can think about it. Anything else?
No, sir. Thank you, sir. Thank you,
so
sir.
maybe it's time. Okay, maybe we should, if you should call it a day. Thank you, everybody. Thanks for the nice questions.
So I just wanted to mention that I posted a link.
Thank you, sir.
Yes, Anirban, please go ahead, Anirban. Let's listen to Anirban.
I just posted a link for this largest LCM question.
Oh, I see. You have a solution to this.
In the chat box. No. I mean, it seems a difficult problem. I just posted a link.
Oh, great. So, yeah. So indeed, I said it is in Anirban's territory and he has posted a link. Okay. That's nice. Thanks, Anirban.
Okay, welcome.
Yeah.
Sir.
And maybe there is
Okay,
an answer
sir.
here
Thank you,
also.
sir.
Thank you. And the next meeting is on Thursday next week, right?
Yes, sir. Yes, sir.
Okay. And
Coming
you will get
Thursday,
the
sir.
coming Thursday, and
Come.
you will get the links on Wednesday morning or something from Dr. Gurusamy.
Okay, sir.
Right? Okay. Bye bye.
Okay,
Now,
sir.
bye,
Thank you.
sir. Thank you, sir. Thank you so much.
Thank you, sir.